All right, limit notation, one-sided limits, graphical and numerical limits. So this actually comprises a few different sections out of the AP syllabus, the College Board curriculum. So let's talk about what a limit is. So verbally, if f of x becomes arbitrarily close to a single number L as x approaches c from either side, then the limit of f of x as x approaches c is L. So if you take a look at this picture right here, what I'm saying is, as I get closer and closer to c along the x-axis, note that if I follow along on the path corresponding, the y values corresponding with the x's, that as x approaches c, the y value on the function is approaching L. And that happens not just on the left-hand side, but if I go to the right of c and I start heading towards c along the x-axis, if I follow that along the path of the graph and I head towards where x is equal to c on the graph, I am heading toward a y value of L. This is what it means for a limit to exist and be equal to a number. All right. So the way we write that, it is the limit as x approaches c of f of x is equal to L. So the limit as we're approaching, that's an x value. So that's my x value right here. The y value, the height that we are approaching, that is a y value. All right. So in order for us to say a limit exists, we have to have both sides approaching the same value. So when we say the limit as x approaches c of f of x is equal to L, what that means is that both the limit on the right-hand side, so right here where you see the limit as x approaches c with the little plus above it, that is what we refer to as a right-hand limit. What that means is you go to the x value c, you go to the right of c, you go onto the graph, and then you allow x to get closer and closer to c, approaching from the right-hand side. We need the limit on the right to be the same as the limit on the left. So this is what we call the left-hand limit. So it's denoted by the little minus above. So if you approach c from the left, that means here's c. You're going to go to the left of c. I'm right there. I'm going to go onto the function, and I'm going to head towards the x value c. What is my y value approaching? In this case, they both approach the same thing. They're both approaching the number L, and so we would say, based on that, that the limit as x approaches c of f of x is equal to L. So really, there's three different kinds of limits. There's a left-hand limit that's approaching from the left. There's a right-hand limit that's approaching from the right. And if those two limits agree with each other, if they are the same, if the left and the right are both the same, then the limit exists. That is called just the limit. It is also known as the two-sided limit. All right, so that's graphically, that's analytically, it's kind of the way it's the way it's defined in the notation. And then here's an example of what we call a numerical perspective. So one way you can determine a limit is you can take a table of values, and you can, if I want the limit as x approaches -7, then what I'm going to do is I'm going to substitute values that are getting closer and closer and closer to -7 from the left-hand side, and closer and closer and closer to -7 from the right-hand side. And if those limiting values appear to be the same, then we would say the two-sided limit exists. Now, what's important about limits is to note that it doesn't actually matter what's happening at c. So the limit is about what am I approaching, not what is it equal to at c. So in this example that I did over here with the graph, it's possible that there could be a hole in the graph right there. And then there would actually be a point way down here. That would mean that f of c is actually, in this case, -4. It would not change anything about the limits, though. The limit from the right is still L, because I'm still getting closer and closer and closer to L from the left-hand side. The limit from the right is still L, because I'm still getting closer and closer and closer. Limits are never about what's happening at the x value. They're only about what is happening as you approach. All right, so let's just look at a couple of examples here. Number one, here's the graph of a function h of x. And I want to use the graph to determine which statement is not true. So let's just go through them. A, does the limit as x approaches a from the left equal the limit as x approaches a from the right? So here is the limit as x approaches a from the left. So I go to the left of a, I'm to the left of a, and I'm heading towards the x value a. I'm heading right towards that little circle right there. So that would be the limit as x approaches a from the left. Here's the limit as x approaches a from the right. So I go to the right of a, I get closer and closer and closer. So the question is, are those two equal to each other? Are they approaching the same thing? The answer is yes, they are approaching the same thing. So this right here is a true statement. All right, so let's go on to B. Is the limit as x approaches c of h of x equal to 5? So here's c. In order for this to exist, see that there's no plus or minus right there. That means we're talking about the two-sided limit. So we need both sides to agree. So here's c. I'm going to go to the left of c. So I'm at x values to the left. I'm on the graph, and I'm going to head back towards c, and I'm pointing right to about right there. And now if I go to the right of c, I'm on c, or I'm to the right of c, I'm on the function, and I'm heading back. Are they headed to the same place? And the answer is yes. And is that place actually 5? And the answer is yes, that is actually at a height of 5. So that means this one is true. All right, let's look at part or C here. Limit as x approaches b of h of x does not exist. All right, well, I'm going to get rid of that so we can focus on this. So it says the limit as x approaches b does not exist. Well, let's look at the limit as x approaches b. Here's b. If I go to the left of b, I'm on the graph, say about right there, and I'm going to head towards b. Looks like I'm heading towards a height of 1/2. And now let's go to the other side. I'm going to go to the right of b. That puts me somewhere up here, and I'm going to head back towards the x value b, and I'm heading towards a height of what looks to be 2. See that there's a gap. There's a gap right here between where the two sides are heading. That means the left-hand limit does not equal the right-hand limit. Therefore, this limit does not exist. So this one is, I'm sorry, that makes it true because it says the limit does not exist. And then finally, does the limit as x approaches c from the right equal 2? All right, so I'm going to cut that out. Same thing. Here's c right here. I'm going to go to the right of c, and I'm going to head back towards the x value of c on the graph, and I look to be pointing at a height of 5. And in fact, we already knew from part B that the limit as x approaches c is equal to 5. What that means is both the left and the right have to be 5. This one is false. All right, so on to number 2. This is a combination of graphs and functions. So use the graphs of f of x and r of x to find a through d. All right, well, the limit as x approaches 2 of x cubed times f of x. So the way this works is if you have a product inside a limit, you can just take the limits of the product. So in other words, we can say, what's going to happen to x cubed as x approaches 2, and what's going to happen to f of x as x approaches 2. Now, in A nice, smooth, continuous function, much like the one I have up here where there's no weird anything's going on. I know I made that hole there, but it's a nice, smooth function. Let's say I was curious about the limit as x approaches -3 right here. So I would be on my graph and I would be heading towards -3 from the left and heading towards -3 from the right. And you'll see that not only am I going to the same place, but that place I'm going to can actually be found by just substituting in the value -3. Now the limit doesn't depend on what's happening at the x value, but in a nice function, the limit will be what's happening at the x value. So the reason I bring this up is because for a function like x cubed, I know x cubed is a nice function. It kind of goes like this. And so I know the limit as x approaches any value is simply going to be the value of the function. So I can just use a direct substitution on x cubed. So I know that's going to be 8. Now, f of x is got some weird things going on, so I need to look at it. So if we look at f of x, what happens as x approaches 2 on f of x? Well, here's 2. So here's 2. I'm going to go to the left of 2. So I went to the left of 2. And then as I approach the x value 2, see that I'm approaching a height of 2. And now let's go to the right of 2. I'm on the graph. As I approach the x value 2, I'm also heading towards 2. Note that f of 2 is in fact equal to 1. That's what this point is right here. But that has no bearing on the limit because the left and the right-hand sides are approaching a height of 2. That makes this limit equal to 8 times 2, or 16. In part B, we have the limit as x approaches -1 of f of x over r of x. So the way we're going to work this out is we're going to consider the numerator to be the limit as x approaches -1 of f, and the denominator to be the limit as x approaches -1 of r. So I'm going to come back up here, delete this stuff out. Now what happens as x approaches -1 on f of x? Well, here's -1. So I'm going to go to the left and then head towards -1. I'm heading to there. I'm going to go to the right, head towards -1. It appears that I am approaching a height of -1. And now let's look at b, the limit, I'm sorry, not b, the denominator now of b. So now we want the limit as x approaches -1 of the function r of x. Here's -1. I go to the left of it, and I head back towards -1. I go to the right of -1 on the graph, and I head towards -1. And it appears that that limit also exists. Both sides are approaching a y value of 0. But we have -1 divided by 0, so this limit does not exist because of the division by 0. C, what is the limit as x approaches 2 of r of f of x? This is a composite of functions. It's a function inside a function. So what we're going to do is we're going to see what happens to f of x as x approaches 2, and that will become the input for r. So as x approaches 2, I need to figure out, and let me write it this way. I'm going to write down the limit as x approaches 2 of f of x is equal. And let's figure that out. So I'll get rid of this stuff. All right. Oh, we've already figured that out. We know, in fact, right here that it's equal to 2. So here's your 2 on f. When I approach and approach, I get a value of 2. So what that means is the inside of this function is going to approach 2. So this whole thing then is going to be equivalent to r of 2, because the inside is approaching 2. And then what is r of 2? Well, here's 2 on the function r. If I go to the left on the graph and head towards 2, I'm approaching 0. If I go to the right, head towards 2, I'm approaching 0. So I appear to be approaching 0. Trying to make that into a nice box. And it won't go. Close enough. All right, and then last one, if you take the limit of a sum, that's just the sum of the limits. So this is going to be exactly equal to the limit as x approaches 1 of f of x plus the limit as x approaches 1 of r of x. Let's look at the graph of f as x approaches 1. Here's 1 on the x-axis. I go to the left and head towards 1 on the graph. I go to the right and head towards 1. I'm definitely approaching a height of 1. And then what's going on with r of x as x approaches 1? So once again, here's 1. I go to the left onto the graph, head back towards 1. I am approaching a height of 2. If I go to the right of 1 on the graph and I head back towards 1, I'm approaching a height of 1. See the separation there. The left and the right hand sides are not going together. This limit does not exist. Thus, the overall limit does not exist.